Yes. Hi, Indira. Thanks so much for your session. If you may allow me to ask, what is the preference for using collab instead of just maybe just double clicking in training your browser? Thanks.
Hi, Richard. I think bit of your question got cut off, but if I understood correctly, you said like, what is the advantage of using Colab over local setups? Yeah, if that's the question, so
No,
for
no, over no, no, over just double click that notebook, and you can just double click the notebook and it opens the Jupyter notebook and it opens in the browser.
yeah, so again, I think I didn't fully understand you. Maybe you can type on the chat. So if you just click on the notebook and yeah, it should open on Google Colab, but the other option is to also use this locally, um, using Anaconda or something of that sort. So both of these options are fine. I think we're just using Google Colab because not everybody might have Python set up on their computers, like using Anaconda so that it opens on the browser. And because later on, when we use these open source LLMs, we will need computing resources that are available on Google Colab and might not be available locally. Okay, good. Yeah, if you have follow-ups, then just let me know. So the other question is Python the language of choice? Um, so I think for what we just did, probably R would make sense as well. I've not used Stata, but I think R definitely makes sense. From what I understand with deep learning and large language models, again, a lot of these models are actually developed in Python, which is why um, when accessing them, they are probably easier to do with Python libraries. Like Hugging Face has a large chunk of its code in Python, right? So I think that's why Python might be better, but I will also mention that there are these R packages for using LLMs. Personally, I don't have a lot of experience with that myself, but I will put this in the chat nonetheless.
Okay. How are you? I'm trying to imagine, or maybe I was curious to know, could this number of, could these matrices like accuracy, F1 score, have less value? Maybe meaning that there was a lot of misclassification, maybe because of the data being not balanced, one, and also maybe trying maybe to figure out on other things that maybe we can be able to use like RAS or reach, so that maybe you can try and see whether the accuracy and uh, F1 score can go high. I don't know. I was only trying to imagine.
No, that's definitely a good question. So I think what you mentioned as lasso and ridge, these are basically parameters for the machine learning classifier, right? So like the optimization function specifically. So for sure, and the suggestion is also usually to try out all of these different parameters. So like in SVM, you have the C parameter and you can try to vary it over different numbers with something called grid search. I'll put the example of that as well and combine this with this cross validation. And so this is how you also find the best hyperparameters for your models, right? So I think for some people, this sounds a bit um, unprincipled, like you're searching for everything until you get something. But in machine learning, this is standard practice. So yeah, I just put in the link to that and you can check that out. But here we just tried the basic version, but you should definitely see what are other hyperparameters that you can change using this grid search to get the best version for your data. Okay,
Thank
I
you.
see a few more questions. So the one is about the qualitative assessment for unsupervised models, right? So for unsupervised machine learning models, these would include things like topic modeling, where we basically take all our text and cluster them into different types of topics. And so there are some quantitative measures here as well. For example, the distance between different clusters of topic. But usually the qualitative assessment is quite important because the quantitative metric might not always be showing matches with real impact. And so in terms of qualitative assessment, what we usually do is that we sample out some of the topics or some of the documents and assign them topics ourselves, and then we see if that matches with what the classifier or the topic modeling algorithm gave us. So that's one way of doing it. The other way could also be just to verify whether the model topics are correct or not. And sometimes you then end up merging clusters that seem very similar to you. So yeah, but like this whole idea of assessing topic models, it's more complicated than supervised machine learning model, which is a bit more straightforward with things like accuracy and precision. But with unsupervised models, it can be a bit more ambiguous. But I will maybe put in one of the papers that I know about systematic evaluation of topic models. Okay. Then, yeah, so the bag of words representation was alphabetical. So, here, like the version that we used, the vectorizer, so there are a few different variants of it. So one is that it doesn't actually do any type of counting. It just checks if a token is there or not. And there are others that actually check for the count. So I will just find the way that you can find the vectorizer count over here quickly. Okay, so that's over here. I just replied to your question in the chat, Thomas. Okay. So for the open-ended classification, open-ended survey text responses classification. So the thing is that, Madeline, for your question, if we use any type of supervised classification, the problem is that we need labeled data, right? So that's why our labeled data corresponded to sentiment. So that's why it was labeled with positive, negative, and neutral. If you have labeled data for like employment, then you can just repeat the exact same thing, replace your data with the data that I have in the notebook. So yeah, again, the problem is that you need this label data, right? But we will see later on when we use LLMs for classification using just prompting. There, you no longer need so much data. Maybe you need 2 or 3 examples, and that is then a lot more flexible. I hope that answers your question, but maybe this will become clearer when we go into the next session as well. Yeah, if you have a research analyst who can manually label the data, then yes, absolutely, you can use the same procedure that we currently saw. Uh, for identification of medical records. So in principle, you can use it for any type of task, right? This depends a bit on how tough the task is. Some are easier than others. Like sentiment analysis is supposed to be easier. And like the difficulty here also might play a role in terms of how much data you need, right? So if you have some label data of these medical records identification, then yeah, absolutely, you can use it for that. Okay, if there are other questions, feel free to put them in the chat, but maybe I will just stretch my legs for 2 minutes and be back at 4:30. Okay, let's get started again. Yeah, if you have any if you have further questions, feel free to put them into the chat. I will now go back to sharing my screen again. Yeah. Let's start again with the notebook. So far we've just seen this confusion matrix, which which helped us get a sense of where our classifier might be going wrong. And so you can use both of these as like complementary approaches to diagnose problems in your classifiers, right? So here we can see that for the negative class, we seem to be doing particularly poorly. And this, to some extent, is also because of which category is underrepresented in your data. And so there are ways to artificially balance the data. You can try to subsample the other classes, but yeah, generally, if you don't have a lot for one particular category, you might not end up, you might end up with a classifier that does not do well for that category. Okay, so yeah, so that was this bag of words classifier that we created from scratch entirely. But you might remember that I also mentioned this other classifier or a dictionary-based classifier that exists, right? So I told you about Vader and that it's been around for some time, but it's still widely used, and it's integrated into this package called NLTK, or Natural Language Toolkit. And we can use um, NLTK to access Vader and then apply Vader also for sentiment analysis. So that's what we're going to do right now. And so we run this, and then here is a single example, which is just like somebody feeling sad. And then we apply Vader on this, so the sentiment intensity analyzer, and we get a bunch of these scores. Um, and so we get 4 scores over here. One is negative, neutral, and positive. And then there's something called a compound score. So there are different ways in which you can use these scores from Vader. The author's recommendation, the authors of this package recommend that you use the compound score and you threshold it. And the threshold, again, might depend on your specific use case, but the rule of thumb is that you can do like -1 to 1. And so that's what we're going to do in this case. We are going to apply this Vader sentiment analysis score on our tweet data and get the results. So that's what we run in this line. Okay, so I see one of you have this example where the compound score is quite negative for hell yeah. So I believe this is because of the word hell in there, which again, it's quite good, but this is the problem with dictionary-based methods, right? That they will obsess over certain words and not take the full context into account. But yeah, maybe some of you can also let me know what other examples you tried and it didn't work out, or if it did. And then if we see the score of this classifier on our entire test set, so that's what we are doing here, right? We're taking our test set that we had previously used in our bag of words representation so that we can get like a fair comparison, right? So it's the same test set that we use for the bag of words classifier, and that's the same thing that we will use with Vader. And here we see that our macro average is actually lower, right? So I think some of you mentioned getting something like 60. I had gotten 60, I believe. Yeah. Yes, I had 60. And so here the macro average is lower. One thing though is that the negative F1 score is higher. So at least that's better. But yeah, generally we see that this is maybe even worse than this bag of words representation that we created. Um, what does macro average represent? So macro average here means that the F1 scores, for example, over here, you just average this out by considering all classes to be the same. So here 0.58 is the average F1 score of these three classes. So there's also something called micro average, which would explicitly take into account the size of each of these categories and weight accordingly. Um, the problem then, of course, is that simply because this is a smaller class, it would count less. And then the higher classes, higher accuracy would distort your results. But again, different use cases might require different metrics. And so that's why you can go to this link over here that I have in the slides. Yeah, so this Wikipedia page about precision and recall, it essentially has all of these different metrics, and then you can see which one might be useful for different use cases. Okay, yeah, so it seems that Vader is not better than our bag of words representation, but can you think of why it might still be useful to use a lightweight method like this as opposed to our bag of words representation? Maybe you can think about this and put it into the chat. About why such methods, even if they don't seem to have like very high accuracy, might still be good things to start out with. Yes, so lots of answers as a baseline, cheap to train, it's faster. So we're not even training anything right here. We're just applying the data fully as is. So in that sense, we don't need any type of labeling data. And it is really quick and it is fully off the shelf. So in that sense, it has some useful properties as a lower bound, right? So essentially, this notebook was supposed to help us think about different lower bounds that can also tell us about how difficult our task is in the first place. Okay, but now that we've seen some of these methods, let's try to look at more advanced methods and see how we went from these basic bag of words representations to large language models. Cool. Let's come back to the slides again. And so now we'll talk about something called vector semantics. Um, Maybe some of you have seen these graphs. These two are supposed to be examples of analogies, where the idea is that men and women have a similar relationship linguistically as king and queen. And the same thing applies for walking and walked and swimming and swam. And then you can also see some of these analogies here, which is with country capitals. Now, with this language contains these relationships between words, right? But so far, our bag of words representation did not care about any type of context or relationship between the words. They were just literally counting how many words were there. So here I want to mention the work by linguists and like people before them, even like philosophers of language, who said that the meaning of words lie in their use, right? And so that's why John Rupert Firth, who was a linguist, had this saying that you shall know a word by the company it keeps. And this was the principle that people used to create more efficient representation of words. So far we had these methods that were entirely based on counting. There was no learning or prediction of the context. And so that's why researchers came up with the idea of learning more low dimensional representations or vectors, which were based on the context. And then this context could be used to predict words in surrounding windows. And so this gave rise to this idea of a word to vec. These were researchers generally at Google who came up with word vectors, where the goal was that each vector, and here you can think of vectors similar to the bag of words vectors that we had before, right? But these vectors should know the context of their words. And you could achieve this by training vectors to predict possible context from words, right? Um, so this goes back to the idea of language modeling, where you have a bunch of tokens and you want to predict the next token. And what do we do with these word vectors? We can use them in our representation. So the classifier part that we had with the SVM classifier, that remains the same. But instead of this very rudimentary bag of words classifier, we can use these better low-level vectors that take into account context. And so that kind of brings us away from these classical NLP techniques where we train separate models for separate tasks like sentiment analysis, and some of you mentioned things like employment or medical record identification. So that was all in the realm of classical NLP, where we trained separate models for separate tasks into what is like maybe modern NLP that has been going on for like maybe the last 10-15 years, where we come up with more general purpose models. And so for that to happen, we needed a few innovations. And so here again, we will take a quick detour away from natural language processing and talk about neural networks and deep learning. So this is the concept behind logistic regression, right? So here we have input features. So those could be our texts. And then we have a classifier. And the whole idea is to learn the parameters of these texts, right? But these features we created ourselves by hand manually. And this can be tedious. So the features that we use for our bag of word classifier were literally each and every word. But I showed you at the very beginning when we were exploring the data, things like how many links are there, how many mentions are there. These could also be features. And then we contrast that with the other paradigm, which is to use neural networks where you don't need to come up with these features. You just given the data and the model is supposed to learn features on its own, right? And so this was like pretty revolutionary. Here again is an example of feature engineering for sentiment analysis that people did. For example, they would look at things like word polarity, unigrams, URLs, emoticons, and so on. And basically with deep learning, you could like totally do away with all of this stuff. You could just give your data to a neural network, and here we have different types of neural networks. And these networks would learn these features on their own. So yeah, so that was one of the big advantages of neural networks and deep learning, which is that they precluded the need for explicit feature engineering and automatically created complex representations, right? And classification was just one type of task that people did, but there were also other stuff, which is like sequence to sequence output, where you have a sequence as an input and you also have a sequence as an output, right? And so this type of stuff would be helpful for machine translation, where you give in a sequence in one text and it comes out in another text. Yeah, so the reason that I bring up deep learning is that it was very important for creating something called contextualized word embeddings. So before, when we talked about word embeddings of word vectors, there were word type vectors, and now instead we are going to create word token vectors, and this might not be clear to you what I mean by that, but hopefully we will see an example that makes it clear. So here we have the static embeddings, or the word to word vector embeddings, and on the right we have the contextualized embeddings. And here we can essentially see that one word type, art, nature, science, religion, they all have a single vector associated with them. Turning on my laser pointer. Whereas here with these contextualized embeddings, we can see that the same words are now being treated as separate tokens. And you can see that nature, depending on its context, can have different vectors. And this particularly becomes important when we see words like art, which of course can mean things like, arts in terms of creativity and creating art. But it can also stand for the Old English R, right? And so here you can see that these highly different meanings of the same token were treated differently in contextualized embeddings. Okay, so what are the axes over here? So this is a representation of these vectors brought down to a lower level. Usually these vectors are like 100 dimensions or something like 900 dimensions, and then you can do like a principal component analysis on them to bring them down into a two-dimension or a two-dimensional representation. And so in that sense, this is the first principal component dimension, and this is the second principal component dimension. And then you can see how the different vectors are placed away from each other. Okay, let me know if that didn't answer your question fully. Okay, so that's how we ended up with these contextualized embeddings, which are much more powerful than these static embeddings that don't take into account the context as much. And that was really helpful, but that was still not enough, because we now have to talk about another innovation, which was called transformer architectures in deep learning. And this was like quite revolutionary, because currently all large language models use transformers. In fact, the T in GPT stands for transformers. So again, I won't go into too much of the technicality here, but the idea was that the transformer architecture basically helped us model context even better. And then you could combine these contextualized embeddings and these transformers to go from specific models to more general purpose models. And so there was this paper again from the people at Google who came up with BERT, which was one of the first models of this type, which were truly general purpose, right? So right before this, we saw this old paradigm where we train a model on a task where we have label data. So that's what we did with sentiment analysis. But now we have a new way of working with these models like BERT, which is that we pre-train this model on a task where we have lots of data, but it doesn't need to be labeled data. It's just unlabeled, because we are trying to learn linguistic patterns, right? Like um, what are the parts of speech? What are the ways that people use slang? When does slang come in? And those types of factors. And for that, you don't need explicitly labeled data. You just need a lot of data. And then once you've pre-trained this model on a lot of internet data, the idea is that it knows a lot about language in general. And then it can be specialized for your particular task, right? So this is called fine tuning. And you can fine tune it on a particular downstream task that you're interested in, such as sentiment analysis. And a little bit of technicality here is that fine tuning essentially means that you take these transformer models and you add a new layer that contains classification parameters. So that becomes very similar to how we have these SVM-like classifiers, and then you end up with a classifier of your own for your specific task. Okay, so now we are going to try this out ourselves practically, and so we'll repeat the same thing as before, but with this new notebook. So again, going back to this notebooks page over here. And that's this notebook now, to huggingface.com or huggingface.ipynb. You can repeat the same thing as before, which is that open with Google Colab. I have it open over here. So this is what this notebook looks like. And here we need to talk a bit about the compute on Google Colab, which is that these models now are way bigger than the SVM model that we used. And so they're going to require more compute. And so it's possible that this might not work on your local if you don't have a GPU. If you have a GPU, that should be fine. And GPU here stands for graphical processing unit. So in that sense, I would suggest trying this out on Google Colab. And here you should try to connect to a specific type of runtime. So here you might not automatically see what I saw before, which was T4. And you would have to go to the run type over here and do change runtime type. And explicitly set this to one of these categories. So I will say here that I have Google Colab Pro, which is like a premium access, which is why I have access to these other GPUs. If you don't have Google Colab Pro, then you will probably have access to one of these. So like either the A100 or the T4. You don't have to have Google Colab Pro, right? You can just follow along right now or use the one that is available. And then you can see if this is something that you find useful, then maybe it makes sense to invest in Google Colab Pro, which is like $10 a month or so. But there are other programs over here. Okay. So has everyone, or at least those of you who are following along with the notebooks, been able to access this notebook and it has opened for you? If that is the case, then I would just suggest running the first 2 lines, and at least that should not throw an error. We are using the same data set that we were using before this, so the sentiment analysis one. But now we're going to try these transformer models on this. So the nice thing about Google Colab is that it comes installed with transformers, so I don't have to do this, but I do have to install this accelerate package, which helps us work with these models better and help speed up inference with them. And so that's running over here. And then you should come till this point and not have faced an error. Okay, if you're not following along with the notebooks yourselves, that's totally fine. You don't have to do anything. But for those of you who are, did anyone get an error, or did they have any problems coming till this point? Okay, so seems like for some of you it's still running, installing accelerate. Okay. Okay, good. Yeah, so you can see that it's also running for me. This should be done in a bit. So I'll talk a bit about the background over here, which is that we're using a model called Distilbert. But like I call this notebook Hugging Face. Are some of you maybe familiar with Hugging Face? Not talking about the Hugging Face emoji, but that is where Hugging Face gets its name from. Maybe you can Google Hugging Face, and yeah, I'll also share the link over here. Basically, Hugging Face is now a company. Before, their whole idea was that they were trying to democratize access to these large language models. And so if you go on this link and if you particularly click on models, you will see that they have like, what, 1,700,000 models, right? So the whole idea is that Hugging Face hosts all of these recent LLMs. So you can see DeepSeek over here. Maybe some of you have heard about that. Then there's Quen. You can search for Llama, and then you will see that you also have Llama from Meta or Facebook. So essentially, Hugging Face hosts these models so that you don't have to host them yourself. Again, these models are huge, right? And it's very difficult to access them so easily. But Hugging Face does that for us and allows us to access these LLMs. Um, and so in that sense, it's really cool. They started out with these transformer models, which are a little different from things like ChatGPT or Llama, but basically they're ancestors in some way. Um, so that's why we use Hugging Face. And so here we will particularly use a model called Distilbert. So I just mentioned BERT, right? It was one of these first transformer models. So if you go to Hugging Face again, and then you search for Distilbert, you will find all of these things. And you can click on this. I'll also put the link in here. Yeah, so here you can check out all of this information about these models. Okay, so there's a question about the size. So the model that we are using, Distilbert, here you can see it has just like 67 million parameters. Here M stands for million. So in that sense, it's quite small and then easy to install. But I think you meant for some of the other models, right? So let's go back to maybe the Llama model over here, right? And so Llama here has 8 billion parameters. So it's a lot larger. Uh, so here 8B does not mean like bytes, like it stands for billions. And if you meant like this other thing over here as the megabyte, 5.98, that is supposed to mean how many times it has been downloaded, right? So this is like 5.98 million downloads, and this one is like a lot lesser and so on, right? But yeah, these models are huge, right? So usually the parameter size is, yeah, so the parameter size is usually measured by the number of parameters, or the size is measured by the parameters. Okay, let's go back now that we've learned a bit about Distilbert. And so Distilbert is essentially one of the most efficient BERT models. It can do whatever BERT can, but it was trained on a little bit less data, but optimized to be more efficient. And it can almost do what BERT can. So there's a bit of like performance difference, but we will see in a bit that it still works. What are parameters? Okay, so that's a good question. Let me show this in the slides that I had when I was talking about deep learning. So here I talked about logistic regression, right? And so here, the parameters for logistic regression are the features that go into it, right? So here for this example, we have 3 features, and each of these features are going to have weights, which will determine the final classifier, right? Just like you can think about it in how we do any type of regression, right? We have like alpha x1, alpha 1 x1 plus alpha 2 x2 is equal to our y, right? Can you tell me what the parameter size was for our bag of words classifier that we did before the break? Maybe you can guess. We do know this, or we saw this explicitly in the notebook. Yes, exactly. So the words, or more precisely, the vocabulary size, which had been like 23K. Exactly. Um, and so our bag of words classifier had a parameter size of 23,000, right? And then you can contrast that now with something like Llama 3.1, which has 8 billion parameters. Like I can't even do that math about how many times bigger that is, right? And if we go back to Distilbert, did I misspell it? Yeah, so if we look at Distilbert and I click on it, then you can see it has like 67 million parameters. That's still big, but that also shows you how huge these models have become. And these parameters, yeah, I also don't know that many words. I think they are outside our vocabulary size. But that's why they need so much data to learn about human language, right? And it's not even just human language. These models are also very good at programming. Some of you said that you were using it for programming. So that's a whole other set of words that they have to learn. So yeah, that's what I mean by parameters. Okay, good. Then let's go back to Distilbert now. So we will use Distilbert for the same type of classification that we've done before with sentiment. But now instead of like a full training, we are going to take our pre-trained Distilbert model and fine-tune it, right? So all of this, or this model is essentially hosted on Hugging Face, and so we are going to access it via Hugging Face. So this line is important for any type of deep learning work because it tells me that the device that I'm using is called CUDA, or that's supposed to stand for the fact that I'm using a GPU now. And so if some of you do this on your local, you should change this. And in fact, if you compare it, like while doing it on a GPU versus on your local CPU, you will see that locally this might take so much longer. This will already take longer than our SVM classifier, but locally it would have taken even longer. Or without a GPU, it would have taken even longer. So we will repeat some stuff that we did before, which was we take this train test split. Again, we want a training set and a test set. And now there are some peculiarities when working with Hugging Face, which is that it doesn't work well with text labels. So here, if you look at the data that we had, it has these labels that are text, right? It's positive, negative, neutral. So we need to convert these text labels into numbers. So that's what's happening over here with something called label encoder. And so we do that. Again, these are like a bit of like formalities. And now we use the tokenizer from Distilbert. So the thing about these LLMs is that, or these models, is that they all have a special tokenizer because they create or they chunk words differently. And so Distilbert has this tokenizer for itself that we are going to use. Again, a bit of formality here is to use the datasets functionality from Hugging Face. This just makes it easier to work with the dataset. So we take the dataset that was in pandas and convert it into a Hugging Face specific version. That's what we are doing here because we have like 6,000 instances in the training data and 2,000 or almost 3,000 in the test. And now we are going to load the Distilbert model. And here we have to specify the model name. We already did that. And we have to specify the number of labels and that this all needs to go into CUDA. And so now we have not even begun training the model, right? And you can already see that this is taking a bit longer. But now we have the model downloaded and we set up a training arguments object where we say that we want to train the model for a specific number of epochs. This is again special for deep learning, which is the number of passes the classifier will make over the full data. And so if you do this too many times, then your model will end up memorizing the data. And that's not very good. We don't want that. We want the model to learn overall patterns instead of memorizing our data, right? So that's why people suggest something between 1 to 5 epochs. And that's what we do over here. And now we set up a metrics object as well because the classifier needs something to optimize for. And so here we're just going to do it more simply and say that just optimize for accuracy. And then we put it all together. So we have the training arguments, the training data set, the metrics. You can also see that our data looks something like this. And after all of this stuff, our classifier is ready to train. This was just time spent in creating our representation. But now I will run this and this will start training. And so for me, this says that it will take something like 14 minutes. This might differ based on the type of GPU that you have. So here, we're still on the first epoch. So let's see how long this takes. I have the output saved in this already so that we can at least see the output. And here there's a bit more like formality, so not super important for the workshop, but like of course important if you want to save the model later on. Yes, 14 minutes for 7,000 instances, that is indeed a long time. And again, you can sort of contrast this with the SVM classifier, right? Which step is exactly fine-tuning the, so this step, right? Trainer.train, this is when the fine-tuning happens. So we don't do any type of pre-training. The model is already pre-trained and uploaded to uploaded to Hugging Face, right? So this is the pre-trained Distilbert model. And then this step is when we do the fine-tuning on our 7,000 instances, and all the stuff before it was just creating the ingredients needed for the fine-tuning. Okay, so yeah, so here, once you're done fine-tuning, you can save this model. You can also reload it later on if you like, and then we will start from here again, which is to predict the results on the test set. So if we add any other data, do we not have to pre-train it? So some people do further pre-train models, but this is if you want to do some type of domain-based adaptation, right? For example, if you want a classifier that is very good at knowing about medical literature or social media literature, then you would take a lot of social media data or medical data and pre-train the model further. So you can do that, but that would require a lot more resources, right? That would certainly take more than 14 minutes. Like Google and stuff who create these models, they basically have lots of GPUs, and even then for them it takes like days to do this pre-training. So yeah, so essentially I think for application-based purposes, fine-tuning more or less is better than pre-training, unless there's really something niche you want the model to do. So yeah. Yeah, definitely. So I do have a slide later on where I talk about resources. Maybe I can show this already while we are training. And yeah, others also should feel free to chime in about your about how you use LLMs. Let me go to that practical step. Yes, so access to LLMs. So we are here currently. This stuff would be later about like commercial options. So we do have like GPU servers in my university and then like clusters. So yeah, that is much better than having to pay for Google Colab, right? And you also have more control, but you can use the same code. Um, so this might depend on how access works on your university, but we usually like submit jobs. If like many people are using it, there's like a priority queue and so on. But yeah, I mean, the simple answer to your question is that we can definitely use university high performance computing in the exact same way. So you would download this notebook and run it as a notebook file or a Python script with your own resources. Yeah, if you have like more specific questions about accessing LLMs beyond Google Colab, then let me know. I'm happy to chat about that. Yeah. So again, this is now 11 minutes. So we can maybe move further on and see what results I already had. So in this step, we actually do the prediction where we take this trainer part, which as you might remember, had all of these ingredients for the fine-tuned model, and then I predict it on my test set. And here, this part is also a bit more complex compared to when we were using SVM. So here we will get probabilities from the model. And in this step, what we do is that we see which model has which class has the highest probability, and then assign that class, right? So you can also get these probabilities from your models, which can also sometimes be more useful than the classes themselves, because that can serve as some type of confidence metric, or you could use it as a continuous variable later on. So yeah, that's what we do in this step, and we then get the categories. But as you might remember, I said that these categories are numbers, right? So we need to convert them back to the text labels. So that's what we do over here using this inverse transform, and then we end up with our final results. And so here again, you might want to contrast this with what we saw as our baselines. So we had the Vader baseline, which here was like 58% as our macro average, and then the bag of words representation, which is like 60%, and that has gone up to 74%. So I can see one of you say that yeah, with a direct prompt-based LLM. So we will see that in the third session as well. And we can make a comparison with this exact data. So I would say that 74 is actually pretty decent. This also depends a lot, again, on the type of task that you're interested in. Some tasks are just inherently harder, right? And this is again not like basic sentiment analysis. This is social media sentiment analysis. So it's a bit more complicated and involved. So there are like people who write papers with 74% accuracy. So here again, it depends on the use case as well a bit, and how much error tolerant you are. But yeah. Okay, so this was the classification report. You probably haven't gotten to this point yet because this is still training. But yeah, if you run it, you should see some result like this. Another advantage of Hugging Face is that they also host fine-tuned models as well, which is that here we fine-tune this model ourselves on our label data, right? But there are others who have created fine-tuned models themselves. So for example, this one, which is also nice because this is supposed to be a multilingual model. And so you can use an existing model and directly apply it on your data. So that's what we've done here. Unfortunately, this is not that good because at least here, the fundamental problem with this classifier seems to be that it's very bad at predicting neutral stuff. And so that really pulls down the accuracy and the macro average F1 score. But this was just an example. There are also a lot more other models. In fact, there are models for many different types of things, right? So if you go to this models website over here on Hugging Face, you can search for things like topic, and then you will see stuff like tweets, Belgium topics, and then there's stuff related to hate speech. I had colleagues who were like really interested in manifestos. And so there are models for this as well, right? So there's one for manifesto-based interaction, and then you have a lot of like language-based models and so on. Okay, let's look at the questions. Yeah, know how much humans agree when labeling this data. Yeah, that's a good question and an important consideration. And I think there is some research that shows that classifier's performance is often correlated with human agreement on instances, right? That they particularly have lower scores on stuff that humans also struggle on. So now there are also like some of these hybrid approaches where the idea is that you see the instances where it has low confidence and you give that to a human. So the human does not have to label everything, but only the low confidence cases. So in terms of practical use of these models, yes, that is what people are doing now, which is that they compare a lot of different classifiers and then they choose the one that performs best. And so here it's also again very important to know um, what the right metric is. So it doesn't always have to be macro average F1 score, right? Like you might value high precision for certain tasks. But yeah, that is usually what people do, which is that they would compare a lot of classifiers. And if they can trust the metric and the test set, then they would say that I want to use the best classifier. The running time of the model, it should not depend on the browser. What it might depend on is the GPU that you're using. So for me, I am using T4. If you use A100, it might be different. So because like different GPUs also have different efficiencies, right? So the better the models, the faster, sorry, the better the GPUs, the faster they will be. Yeah, it shouldn't depend on the browser though. Okay. And how much time are you getting? Yeah, it should not exceed like probably 20 minutes. I think between 14 to 15 might make sense depending on the type of data that you end up with. But yeah, really, if it's like 3 times higher than this, then yeah, so similar to mine, right? Also with T4. Okay, done in 16. Great. So maybe let's come back to this in another 5 minutes when a lot of our classifiers should be done. And let's go back to the notebooks again. So I had left off here. And so, yeah, so we talked about these two types of paradigms, right? The unsupervised one and the supervised one. And we tried all of these different variants with the supervised one, where we started with this super simple bag of words representation. Then we tried this more complex Distilbert representation. But we also saw a few off-the-shelf techniques. So here the idea is that these were models that were perhaps created for other contexts, but you still need to kind of see that if they can be adapted for your context, right? So you need to see if they can work well. So you still need a test set. So one example of this was Vader. So we have arrived at this point, right, where we have these fine-tuned, pre-trained language models like BERT or Distilbert as we used. And so BERT was kind of the rage before ChatGPT came out, right? Like whenever we had any type of NLP tasks, previously people were like really creating a lot of like handcrafted models, but now BERT was like the go-to method. Like you had to try BERT or its variants, like Distilbert. And it was still tractable. Like we can still use Google Colab to do this. It would also be possible on our local machines. You would maybe need 3 hours, but it was still doable, right? Um, and so now from there in 2 years, we came to ChatGPT, right? And so the idea behind what is called an LLM is sometimes a bit controversial. Like sometimes people say that models like BERT are already large language models. Like you saw that they had like millions of parameters, right? So I guess it's not wrong, but I think when people say LLMs, they usually mean LLMs that can be interacted with via a prompt. So that is not the case with Distilbert or BERT, right? We can't interact with them with prompts. But now we will talk about models that can be interacted via prompts. So again, we already talked about language modeling. So this is just a bit of a quick recap over here, especially these parts, right? Where we want to create a model of language or speakers of a language so that we can create a less complex version of it so that we can study it or even predict future behavior. And we saw all of these things about using probabilities and chain rules to predict content. URL to the slides. Yes, 1 second. I will just share the link to the material which has the slides. Okay. So there is one very crucial aspect of LLMs that we have not talked about at all. So far, we were just always talking about classification. Um, but there's one other fundamental pillar of natural language processing, which is natural language generation. So we don't just want models to understand language, we also want them to produce it, right? And you can see that that is fundamental in models like ChatGPT. So we want systems that can produce fluent, coherent language that is fit for human consumption, like actually interact with humans through language. And so uh, we roughly talk about two types of generation. Open-ended generation, where the output distribution has some kind of creativity and is not fully constrained by the input. And then we have non-open-ended generation, right, where the input mostly should determine the output. And so you have these less open-ended cases like machine translation, where of course you don't want the classifier to like invent new things when doing translation, right? But then you have on the other end things like creative writing or storytelling. And here you want the LLM or the machine to be more creative and take more liberty. Of course, it's easy to classify this in theory, but in principle, it's very hard, which is why we have one big issue with current LLMs, which are hallucinations, right? That they hallucinate entirely new facts. And you can think that this type of creativity or creative license would be perfectly fine for story generation, novel generation, screenplay writing. But you don't want that when you're asking the LLM for factual knowledge, right? So this is really difficult to implement and constrain. Um, but let's talk about how we have these generative LLMs now from these other LLMs that existed, right? So we had BERT large. So we were just talking about BERT. And then we have GPT-3, GPT-2, Palm, which I think was like basically a version of Gemini, like a precursor of it. And so, of course, this is time, and you might have already guessed what this is. These are parameter sizes, right? So these are the sizes of these models, and you can see that these models are growing larger and larger. And apparently, scaling these models up by training them on so much data, like usually pre-training on them on so much data, gives rise to something called emergent properties. Okay, so a question on which LLMs to use and why. So this is a very, very critical question, and unfortunately, I think the answer is not so straightforward. So there is something called, well, at least it used to be called Chatbot Arena, or no, it's still called Chatbot Arena. And here you can go to the leaderboard of this Chatbot Arena, and you can see which models are performing the best. And The way that the evaluation works is a bit tricky, and recently there has been some criticism that commercial models have a tendency to game these leaderboards. Um, so yeah, so take this with a grain of salt, but apparently this is one of the best ways to determine this, especially now that we have so many models. But yeah, so we have these leaderboards which are updated daily, and apparently here on this arena, people go head to head, comparing the output of different LLMs, and they don't know the LLM family or the exact model, right? And so in principle, they do a blind test, and that is what ends up determining these rankings of models, right? And so here you can basically see that the commercial models really dominate these leaderboards. Um, Again, take that with a grain of salt. But here at least you can see things like DeepSeek is also there, which is not entirely commercial. So I would say this is one example. Again, depends a lot on the type of task that you're trying to do. And I don't think it's unfortunately very clear yet, which is a superior model. But there are leaderboards like this. There's another leaderboard called HELM, or Holistic Evaluation of Large Language Models. This is also another leaderboard that you can check out, um, where you can see how LLMs are performing with each other, against each other. And this one also divides it based on different capabilities like content analysis of different types and information search and so on. Okay. Yes, let's go back again to the emergent properties of LLMs, where the idea is that apparently the more data you train these models on, the better they get. But they apparently have emergent properties, which is that apparently they learn to do entirely new tasks without any type of fine tuning, right? So that's what I mean over here by gradient updates. So gradient updates could also be thought of as parameter updates, like where we are creating the parameters of the model, or the parameter weights of the models. Um, but apparently, like LLMs, at least from like GPT-2 onwards, they start saying that these models can do tasks that they have not been fine-tuned on, right? They can see a couple of examples and learn entirely new things. So that's why this was a paper from the people at OpenAI, and they said that language models are unsupervised multitask learners. So there is still some debate about whether these emergent properties are true or not, but to some extent, this has given rise to a lot of like prompt-based interaction with LLMs. And so that's where these emergent zero-shot and few-shot learning capabilities come in. And I'll mention very soon what I mean by zero-shot and few-shot. So here, this is also called in-context learning, which is that you give some examples or shots, and a classifier will learn what to do, or an LLM will learn that task just from those examples instead of so many fine-tuning examples, right? And zero shot is even more extreme because this means like no examples. You just tell the instruction, like you tell the model to classify something as positive, negative, or neutral, and it should be able to do that on its own. And one important thing over here is instruction fine-tuning. Um, Maybe we will take a quick pause here to see if our classifier has trained already. So I will switch to Google Colab. And so, yeah, I can see that that's done. I think that should also be done for many of you. So I will just maybe demonstrate the rest of this notebook quickly, because at least this step is important so that you can access the model that you just trained. And on Google Colab, you can see the files. And so here you will see that there's this new directory created called output HF, and this has your model in here. And you essentially need this part to get the model again so that you can use it later on. And here we will see some results. So here you can also see that even prediction is not that quick, right? So here the prediction is going to take a few seconds. And I'm just going to run this quickly, and we can see the results in a bit. Did anyone's notebook throw an error for those of you who were running this yourselves? If it did, let me know. Okay. So far seems like it worked, and here we can see the results. And again, right, like the average accuracy and F1 score is higher than the bag of fuzz representation. We still see that it's poorer on the negative class. Okay, let me do the label encoding so that it's easier to see. So here we can see the labels back to their text versions, and here we can see that it's 67, so that's worse still for the negative class, but generally the numbers have gone up, right? So yeah, that's good. And maybe you can let me know how your classifiers did as well. So that was BERT, or DistilBERT to be more precise, which is again similar to models like ChatGPT, but not quite there because those models were trained on more data. They were um, created for natural language generation, which BERT is not. And then so that they can actually talk to us and answer our requests, we had to do something called instruction fine tuning. So this is the same type of fine tuning that we just saw, but um, it has a very peculiar nature, which is that we are now teaching the model to answer our instructions rather than do sentence completion. So what do I mean by sentence completion? So let's say we have a prompt like this, explain the moon landing to a 6-year-old. The output of models like GPT-3, which were generative models but not instruction tuned, would be that they don't actually answer the question. They just give you variations of this, or they try to complete the sentence. Like they're thinking that, yeah, this is a starting prompt and I just need to complete it further, right? Because this is very much the goal of language modeling, which is that given some part of content, you predict what comes next. That is not what ChatGPT does, right? If you ask ChatGPT this question, it will answer this question. It will not complete that question. So that's where we did this step called instruction fine-tuning, which is to train language models to follow instructions with human feedback. And so we no longer did what we did before, which is to pre-train a model and then fine-tune it for a specific task. But instead, we just taught the model how to answer instructions via natural language. And so there was this model called Flanty 5 that we will see as well. It's also from Google. And what Flanty 5 was taught to do is that you gave it labeled examples like this, and here the labeled examples are stuff like that, right? So here is the uh, instruction, and here is the answer to that instruction. So yeah, here you can see all of those examples, and then you can test the language model on totally unseen tasks, right? So here we have like a what if scenario about George Washington meeting this modern scientist, Geoffrey Hinton, and the LLM, which has never been trained to do this, should be able to do this, right? So this was pretty um, different from what we'd seen so far, right? Instruction fine-tuning. So we are supposed to go into a break in a bit, but maybe I will just complete the instruction fine-tuning part. And so, yeah, this way we were able to teach models to follow our instructions. And then we also had another step, which is reinforcement learning through human feedback, which is that instruction fine-tuning was still not perfect at satisfying human preferences when it came to LLM interactions. And so that's why people used reinforcement learning, where the idea was that humans interacted with these LLMs and told them that, hey, this answer that you just gave me, it's not very good, but this other answer that you gave me, that's better. And those of you who interact with ChatGPT, you see this because sometimes it happens that it shows you two answers and it tells you to pick the answer that you prefer more, right? So that is this step, which is reinforcement learning with human feedback so that we can tailor the LLM even further to what people want. And so all of this went into an LLM to create the modern LLMs that we have, right? So you have this part again, and before the LLMs were doing text completion, but now they actually follow our instructions and answer our questions. So this way we have come up with the at least LLMs that are widely used, like ChatGPT. Of course, these LLMs like GPT-4 are even more complicated, and it's not really clear what goes into them. So all of these processes like RLHF or reinforcement learning with human feedback, it's not super well documented. We also don't know what type of data is used. But for a lot of open models, we do know them. And so now we can finally use models like this for things like prompt-based labeling, right? We don't have to train any classifiers anymore, but we can use prompting to get them to do the same tasks. And of course, this has opened up a lot more options. There are all of these different ways of doing prompting. Like people say now, the hottest career has gone from being data scientist to being a prompt engineer. And so lots of people are working on how to come up with good prompts, right? And so what we will do in the next hands-on session is prompt-based interactions with the models. So we are still going to use Hugging Face and this model Flanty5 that I just mentioned, and use it to do sentiment analysis instead. Yeah, so I would say that maybe we take a break now and come back in 15 minutes. And again, as before, if there are questions, we can, I'll stay on for like 5-10 minutes to answer them. And I'll stop sharing my screen and just put in the chat that we come back in 15 minutes. So that's for me, 5:58 CEST. Okay. Okay, questions. What does a prompt engineer do? So I don't know how your experience is with working with these LLMs and prompting them, but like even like really the smallest changes, like just adding a full stop sometimes can lead to highly different results. And so prompt engineers are supposed to figure this out, like how do you optimize interactions with these models so that they actually do what you want it to do. And then there are like so many complex multi-step tasks, right? Like, do you feed in all the information in one go? Do you do it by step? So I imagine those are the things that prompt engineers do, though I'm not a prompt engineer myself, so I cannot definitively say. Okay, other questions.